Today's topic is liquid pressure. And when you swim to the bottom of the deep end of a swimming pool, you know that there's pressure down there. Your ears hurt, and the deeper you go, the more pressure there is. So here's what we want to do. We'd like to be able to identify the variables that affect liquid pressure. And once we identify the variables that affect liquid pressure, we must be willing to exclude all other variables and be able to say this affects it, but nope, that variable has no bearing on it. And then we're going to use those variables to develop an equation that will be able to calculate liquid pressure. And then we want to be able to make sure we use the appropriate units in that equation. Now, let's just remind ourselves about pressure in general. That if this brick is 5 pounds and that brick is 5 pounds, which brick puts more force on the surface? And the answer is the same, because both put 5 pounds of force. But this brick is touching the surface in a much smaller area, so we got 5 pounds concentrated into a small area. That's going to be a lot of pressure. And so pressure was defined as how much force there was per area. We should measure force in newtons. We should measure area in square meters. And newtons per square meter has a common unit, and that's called pascals. All right, so let's see if we can kind of think on our own a little bit what variables affect pressure. Let's see, these are bricks, and we're looking at the pressure between this and the surface, or the pressure between those two bricks. So right now we just have one brick here and one brick there. There's pressure. If we stack another brick on top, we get twice as much pressure because there's twice as much force in the same amount of area. Or if we go one brick deeper, again, we got twice as much pressure. If we stack two more, now we had 4 instead of 2, twice as much pressure again. And if we go 2 deeper, now we got twice as much pressure again. And we put 3 on top or go 3 deeper. So one variable that affects how much pressure you feel when you stack things on top of each other is depth. So just how deep you go. The deeper you go, the more stuff is stacked on top of you. And you can think of a dog pile. If you've ever done that, not maybe what you were thinking, maybe something more like this, but hard to tell who's on the bottom. I'm not sure if it's the black cleats or the red cleats, but the guy in the bottom has the weight of all the people on top. This guy just has the weight of the one person on top. So the deeper you go, the more stuff is on top of you. All right, so depth is one variable. Now, let's say that we had these bricks that are made out of granite, and these bricks are made out of wood. Everything else being the same, one variable that affects the pressure is the density. That if this has the same volume as that stuff, the more dense that material is, it's going to weigh more. It's going to have more mass too. So density is another variable. All right, lots more force over that same area. Now let's say we have a chunk of water here, and same thing happens. The more water you stack on top, the more and more pressure you feel, and that's just because all that water weighs more force in that area. All right, but let's see if we can go ahead and develop an equation that relates those variables. So pressure was just force over area. And then let's see if we can get a little bit more detail on what force is. Newton's second law says it's mass times gravity. Or if you take kilograms multiplied by meters per second squared, you would tell you how much newtons of force there is. So we're going to take force and we're going to substitute in mass times gravity. Now we said density was one of the variables, and let's see if we can calculate the mass based upon the density. Density was defined as mass divided by volume, so mass should be density times volume. We're going to substitute in here density times volume, and then we still have gravity. Now when we talked about the area, that was the area of the or we can find the volume of this shape by taking the area of the base and multiplying it by the height. So if it's a cylinder, you would just find the area of that circular base multiplied by the height. But in general, volume of a prism is area of the base times the height. So we're going to substitute volume for area times height. And in our I can statement, we identified one variable, or we were hoping to find a variable that does not affect liquid pressure. And can you see what that variable is? And it turns out area does not matter. There's area in the top, there's area in the bottom. So it is a variable that does not matter. The only variables that matter is density, the acceleration of gravity, and how deep you are. And we usually put density, gravity, and height. Now, if we're going to put letters to represent these concepts, H would be a good letter for height, or sometimes we use delta Y, a change in the height, lowercase g for gravity, and then you might remember a good abbreviation for density, and that was the Greek letter rho. So rho, g, h is the variables that are used to calculate how much pressure there is. So swimming to the bottom of a swimming pool, you'd have to know the density of the water, the acceleration of gravity, and how deep in that water you are. So pressure is rho g h. We can look at the units of that. Density was how much mass there was per volume. Gravity is the acceleration of gravity, meters per second squared, and height is just measured in meters. So density, gravity, and height. It looks like we got meters squared in the numerator, meters cubed in the denominator. So that's going to cancel and just leave us a meter in the denominator. And that is the same units for pascals, 1 Newton per 1 square meter. And this is a pretty common equation. If you were an engineering or science type, you could say if you're feeling stressed or feel like there's just too much rho gh, this says this is too much, I just can't handle the rho gh, we're saying we can't handle the pressure. Let's look a little bit more about density and different units, particularly for water, because a lot of the examples we're going to look at involve swimming to the bottom of a swimming pool or diving deep in the ocean or something. So if I had a cube here that is 1 centimeter by 1 centimeter by 1 centimeter, that's a cubic centimeter. Turns out that's also the same thing as 1 milliliter. It's kind of neat that we could take this unit of volume, a milliliter, and compare it to units of length. Length, width, and depth also make a volume. And then if we had 10 of those along the bottom, 10 along this side, and 10 here. So if I had a cube that was 10 centimeters by 10 centimeters by 10 centimeters, 10 times 10 times 10 is 1,000 cubic centimeters, which, because 1 centimeter is 1 cubic, 1 cubic centimeter is the same thing as 1 milliliter. 1,000 cubic centimeters would be the same thing as 1,000 milliliters, and that's the same thing as 1 liter. Okay, but that's still not MKS units. We have to get things into meters, kilograms, and seconds. So if that was 10 centimeters by 10 centimeters by 10 centimeters, it would be a liter. And if I lined up them all along a meter, 10 of them would fit along this dimension here. So that'd be 10 liters, all on a line there for 1 meter. And then we get 10 along here. So we had 10 here, 20, 30, 40, 50, 60, 70, 80, 90, and 100. There'd be 100 liters down there. And then if we stacked them up here to get a volume, that's 1 meter by 1 meter by 1 meter. That's 100, 200, 300, 400, 500, 600, 700, 800, 900, and 1,000. So 1 meter by 1 meter by 1 meter is 1,000 liters. And we know what 2 liters looks like. So 500 of those could fill up that volume. And 1,000 liters is the same thing as a cubic meter. And remember that 1 milliliter is the same thing as 1 gram. And maybe you don't remember that, but 1 centimeter by 1 centimeter by 1 centimeter, a cubic centimeter, if that was made out of pure water at 4 degrees Celsius, it would have a mass of 1 gram. And 4 degrees Celsius is the most dense water will be. That as the temperature cools down, it gets more and more and more dense. But remember, frozen water is less dense than liquid water. And from here, it starts to form a crystalline structure and begins to freeze. But at 0 degrees Celsius, it is frozen. So if 1 milliliter is the same thing as 1 gram, 1,000 milliliters would be the same thing as 1,000 grams, or 1 liter of water has a mass of 1 kilogram. So if this is 1 centimeter by 1 centimeter, I said that wrong. 1 meter by 1 meter by 1 meter, that's 1 cubic meter. That would be 1,000 liters or 1,000 kilograms of water. It's called a metric ton. 9,800 newtons, because remember, 9.8 newtons is the same thing as a kilogram. So if we're going to plug numbers into this equation and we want to calculate how much pressure there is at the bottom of the deep end of a swimming pool, should we plug in the density of water, which is 1 gram per milliliter, 1 kilogram per liter, or 1,000 kilograms per cubic meter? These are all appropriate units for the density of water. But if we're going to stick and make these units work together, we have to use the MKS units, meters, kilograms, and seconds. All right. And then this would be a weight density of the water, the weight of that water per volume. One thing is what's different about liquids and gases, by the way, liquids and gases both fit into a category called fluids, but the difference between that and solids in terms of pressure is that a solid only puts pressure in the downward direction because gravity is pulling down. But liquids and gases redistribute that downward pressure into pressure in all directions. And it comes from a microscopic view of the little water molecules that are bouncing into each other. And if you place an object, like this is the swimming pool and you are the object, the pressure you feel on a microscopic level comes from the sum of all these little collisions of all these little molecules. And maybe that makes also sense of why density is a factor, that if these molecules were more massive and they collide into you, well, they're going to put more pressure in a given area. Gases, the molecules are a lot farther apart, but they're moving much more freely. But again, if you have an object submerged in a gas, there's going to be pressure against that object because of the collisions of the molecules. And those molecules are moving in all directions, so the collision could happen in any direction. So if I had a little flask like this with holes drilled in it and a plunger pushed with downward force here, and it creates water spewing out there, which is obvious, but it suggests that even though gravity is only pulling down, that pressure is redistributed in every direction. So solids are only going to have, these are rocks that got compressed because of the weight, but that was in the downward direction. And liquids redistribute that in every direction. This is a styrofoam head from a mannequin, and if that was submerged in the ocean, the pressure would be in all directions on that. So here is that taken down to 2,000 feet below the surface, kind of crushed it, but from every direction. Now it's taken to 6,000 feet, and there was a lot of pressure on that, taken all the way down to 9,000 feet. That's almost 2 miles. That's pretty deep in the ocean. So liquids, pressure is in all directions. Solids, just pulling it down. The deeper and deeper you go, it's just going to squish it from above. Grain silos grain behaves like a liquid. Open the door here and it will flow out just like a liquid. But you can see that the bands here are much closer together and they're much further apart up here. That's to be able to hold that whole silo together from the greater amount of pressure. So let's look at this here real quick. If we were to graph depth on the x-axis and pressure on the y-axis, the density of that fluid is a constant. It doesn't change. And the acceleration of gravity is a constant. It doesn't change. So you multiply those two constants, you get a new constant, and it looks like we have the equation of a line. That height is graphed on the x-axis, pressure is graphed on the y-axis, and the combination of those two variables create the slope of our line. So if we were to graph pressure versus depth, it's going to be a linear relationship. And that's going to be really important to remember when we start talking about buoyancy. So the deeper and deeper and deeper you go, the more and more pressure it is, but it is a linear relationship. If we just take that whole thing and stand it on end, and we drill a little hole here, there's some pressure. Drill a hole twice as deep, there's going to be twice as much pressure. 3 times as deep, 3 times the pressure, and so on. The deeper and deeper you go, the more and more pressure there is, but it is a linear relationship. So this is the Hoover Dam, and water is spewing out here because Lake Mead is up there when it's full. It's down here about now. It's really low. But drill a hole in the side of this thing, water kind of trickles out here, shoots out there, shoots out there. But if you continue all the way down like this, like if we put that thing way up here, that's just a tiny little thing. We've gone a lot deeper, tons of pressure. So here's what Lake Mead looks like when it's nearly full. And this is what it looks like in the Colorado River there. It's about 700 feet deep. And that's really deep water. In fact, just to put it in perspective of how deep that is, if you were to get your scuba diving license and you just get your Open Water 1 scuba certification, you're only allowed to go 100 feet deep. And if you go 100 feet deep scuba diving, that is deep. Okay, so here's what Hoover Dam looked like as was being made. It's just the width of the road above, about 727 feet deep, but at the base, it's about 660 feet thick, and that's just to handle that fantastic amount of pressure. And that pressure is used to push water and turn these turbines that produce electricity. There's a bridge now that goes across this. It's a pretty fantastic bridge. But this is Lake Mead, and all that water is being held back by the dam there. If Lake Mead did not look like that, but rather looked like this, what do you think would happen to the pressure against the dam here? And I'm hoping you said nothing. The pressure would be no different because we've identified the variables that affect the pressure. All other variables don't matter. The only thing that affects the pressure against the dam is the density of that water, the acceleration of gravity, and how deep that water is. So if you were to take a garden hose, remember this is about 700 feet deep. So if you take a 50-foot garden hose, connect 14 of them together, and take your thumb and push on the bottom of that garden hose, and then just take a pitcher of water and pour and fill that garden hose up with water, what's it going to be like trying to hold your thumb against that garden hose? Well, it's going to be pretty similar to try to hold that back there because those are the only variables that affect liquid pressure. Often we think about submarines going really, really deep in the water, and we think if they go too deep, they will implode. And it turns out that probably is not what actually happens, that if this goes so deep here and the hull begins to break down, the moment the hull cracks, that pressure will just fill that water, or the water will fill the inside of that submarine almost instantly, just like being filled. And that's only 700 feet deep. If this is like 2,000 feet deep, there's going to be even more pressure like that. So you probably wouldn't die from being crushed by the submarine collapsing. It would be just the crushing force of the water rushing in. All right, now let's just challenge ourselves this idea that density, gravity, and depth are the only variables. Swim to the bottom here, swim to the bottom here. The pressure under this much water is going to be the same as the pressure under that much water. The area of that does not matter because these are the only variables that matter. Now, an interesting example of that is I have a sailboat and I wanted to put a freshwater reservoir on the bottom of the boat and then have a through hull fitting or through deck fitting that I could pour water into here and it would fill this expandable bag. So when there's water in this tube here, there's pressure on that bag. But surprisingly enough, if this is at some distance here and we start to fill that thing up all the way up to up here, that's going to be 6 times as much pressure in here. And when I fill this up, I try to be careful to only fill it to here, not to fill it up into there. Even though that doesn't seem like much water, that pressure gets redistributed all through here, and it could actually burst that bag if I'm not careful. Again, surface area does not matter. Swimming to the bottom here, same pressure as swimming to the bottom there. These are the only variables that matter. And it's the vertical distance. Because this is a long distance here, and because gravity acts in the downward direction, we're just measuring how far down we have gone. So if you wanted to calculate how much pressure it's going to take to pump this water up over this hill, it's not the length of that tube, it's the vertical height that goes there. One thing that's interesting here in Colorado in particular is that a number of places there's artesian wells. An artesian well just means that if you put a pipe and drill down into the water there, the water that you hit is going to be under pressure, and it's going to just naturally spew out of the ground under pressure. Reason is we have a lot of clay in our soil, and if there is a depression here and this is clay all in through here, an impermeable layer, and then this is some sort of gravel or some permeable layer where the water could collect, this clay here prevents the water from filtering into this area here, and if this is the ground level, this water here, this extra height of water here created pressure that made it spew out of the ground. So if you look at, because there's pressure here, that layer probably came from the water that's up higher above that level there. And Fiji water, I don't think it tastes that great, but it advertised, ooh, it's artesian water. And that just means that it came out of the ground easily. It was under pressure. Doesn't mean much else. So to get pressure in our water faucets and stuff, we have to elevate our water up above there so there's a distance and it will spew out. And if you look across the horizon there, we see all these water towers, and that's just so we can get the pressure in our systems. If you want to take a shower and there's lots of pressure, you'll find there's more pressure in the basement or in the basement or on the first floor than there is on the second floor, because that water tower out there, well, you're just not as deep. Connecting it to the medical field, you always take your blood pressure right here in your arm to measure the pressure of the blood, which is going to be at the same depth as your heart. You could measure the pressure in I think it's called your brachial artery, and you can measure it in your ankle like this, but you would just have to lay down so that that blood pressure cuff is at the same depth as your heart. A fun magic trick you can do is put a penny in your hand or in someone's hand, and then you have to guess which hand the penny is in. What you do, though, is you turn your back so you can't see, and ask the person to put the penny in to raise the hand that the penny is in, and keep that hand well over their head for 20 seconds or so everybody can see which hand it is in, but you can't see because your back is turned. And then you ask them to bring their hands down side by side, and you have to guess. But one hand is going to be real pale, and the other is going to be real pink with blood. And the hand that is more pale is going to be the one that had the penny in it, because that had a lot higher blood pressure. This hand was down by your side. All right, some interesting things that if we were to drill a hole in the bottom of a water bottle here, water's going to spew out. That's if we have the lid off. But if we drop that thing, what's going to happen to the water spewing out? Well, it's going to stop spewing out because we're in like 0 G's if it's in free fall. It's quote 0. If you let the water spill out and then let it drop, nothing here until it hits, and then it shoots out really big. And that's because when it hit the ground, it had a really big acceleration, which is going to really increase the pressure. And then if we had if we swam 50 feet under Lake Michigan, or 50 feet under San Diego Harbor, there is going to be more pressure under San Diego Harbor. I guess you'd have to know that Lake Michigan is a freshwater lake and there's no salt in it, so it makes that water less dense. If we were to swim 10 feet to the bottom of a swimming pool or 10 feet into here, as long as the density of that water is the same, the amount of pressure you feel under this swimming pool will be the same as under that big swimming pool. Surface area does not matter. And that is all I have.